All right. So I'm Will, and I've been doing miniKanren for 10 years. miniKanren is not a logic language, so I'm not going to be talking about logic programming tonight. So if you want to hear about logic programming, too bad, because I don't believe in logic programming. Well, maybe I do, but not for this. So I'm talking about something I call relational programming, which is related to logic programming, but sort of a different take, sort of in the same space, and often gets to the same point, but it's a little bit different. When I first went to grad school, Dan Friedman was my advisor, and I met him and said, Dan, I'm so glad to come to IU and finally learn Scheme, advanced Scheme hackery under you. And he said, I don't do Scheme anymore, I do logic programming. But he was lying because he actually does relational programming. So anyway, you're not going to learn about logic programming tonight, too bad. Anyone here done Prolog, by the way? Couple of people? Okay, that's logic programming, that's not what we do. We're going to do something more disciplined in a way. Harder, arguably less useful in some cases. So, maybe not arguably. But I can show you that miniKanren actually is useful because it's been ported to many languages, including, the other night, PHP. Right? So it's got to be good. Yeah, Facebook. So miniKanren.org if you want to find out more miniKanren stuff. miniKanren is an embedded domain-specific language. Actually, it can be used for logic programming. It can be used for Prology type things. But it also supports another style of programming, which I call relational programming, which is sort of the pure version of logic programming. Because the logic programming as it's typically used, the analogy I like to make is that logic programming as practiced in the Prolog community is sort of like how functional programming was practiced in the days of Lisp before we had things like Haskell, right? So it's the sort of thing where, yes, you're encouraged to program in this nice functional style, but if you ever run into trouble or you need some extra efficiency or something like that, there's always a side effect waiting for you, right?
We're talking about scaling.
Yes, well, lots of these languages, right? And then what happened? So Haskell came along, and why did they get rid of effects? They got rid of effects because of laziness. So they didn't really have a choice. Okay, and sort of they hid the effects in monads and things like that. But when Haskell came along, then even people who've been programming in a functional style for a long time kind of have this epiphany like, oh, okay, you really can be pure, right? And interesting things happen when you restrict yourself to being pure. There was a lot of innovation in functional programming when Haskell came about. So I see that miniKanren and relational programming is sort of the same way. So we've had logic programming for a very long time, since at least, say, the mid-70s, if not beforehand. But in the way logic programming is usually practiced, you'll start off with some beautiful formula in first-order logic, let's say, that describes your domain. Maybe you're doing like a rule-based system, maybe you're doing an AI system. And then you'll translate your beautiful first-order logic formula into Prolog and these horn clauses. If you've done Prolog, you know what that is. And then you want efficiency. So you start adding these things called cuts to prune the search tree. And then you want some other things. You want to deal with arithmetic in a certain way. So you start projecting numbers using is. And then you want this other thing. So you want to handle negation in a certain way. So by the time you're done, you add all these impure features to your program. And now it no longer has this sort of beautiful declarative interpretation. Okay, sort of like taking a beautiful scheme program written in this purely functional style and then adding set bangs all over the place. Okay, so that's why I make a distinction between logic programming as practiced, say, in the Prolog community and this relational programming. Okay, so miniKanren is an embedded domain-specific language. So it's embedded in, what I mean by that is that the Scheme version of it is written as a series of Scheme functions and Scheme macros. So you can, any conforming R5RS or R6RS Scheme implementation, you can just add the miniKanren definitions, and then you have Scheme and you have miniKanren. And they talk to each other according to this well-defined interface using this run operator. But it doesn't have to be embedded in Scheme. You can embed it in all sorts of other languages. So the primary embeddings are in Scheme, in Racket, There's an implementation called miniKanren that Claire Alvis is working on at Northeastern. There's another implementation called core.logic, which is in Clojure. In fact, most people using miniKanren, I think, are actually using core.logic in the Clojure version. And a lot of those folks use core.logic like an embedded Prolog. Okay, they use it very much like Prolog. They're using things similar to cut to prune the search tree to get efficiency. They're using some of the operators that I consider impure, but that's fine because it serves their needs. So if you want something like a Prolog in your language of choice, miniKanren might be useful for that. Or there are all sorts of lots of embedded programs. I'm not here to sell miniKanren. If you want to use miniKanren, that's great. Logic programming as a paradigm, I think, is extremely interesting. So I think logic programming is like the big idea, not the miniKanren stuff. Okay, but we have sort of a different take on logic programming with miniKanren here. Yeah.
So curious about the name Kanren. And I suppose there's a big Kanren because this is a mini one.
There was a big Kanren. Now there's a miniKanren. Now there's a miniKanren, which is microKanren. See where this is going. So Kanren. So when I originally was doing this work, it was with Dan Friedman and Oleg Kiselyov. Oleg is from Russia, and he also speaks Japanese. And Kanren, well, originally he wouldn't tell me what Kanren meant. I assumed it was some unspeakable Russian obscenity. It turns out it's not, it's Japanese. Anyone know any Japanese? Anyone know Kanren? Apparently it means something like relation in Japanese, but I've also been told by a Japanese researcher it's more like monad. I don't know. I don't know enough about Japanese, but so it's a Japanese word. So I like to think it means relation. There was a Kanren. Kanren was like a full language. That was much more like Prolog, and it had all sorts of optimizations you had in Prolog and things like that. Okay, so if you really want a Prolog in Scheme, there are some other Prologs out there, but you might want to look at Kanren. It turns out that what's happened is the miniKanren was sort of like this very small implementation of the core ideas, and to some extent it almost looks like Kanren that's been compiled, right? Like sort of like the low-level stuff. But then when you look at core.logic and the pattern matching on top of core.logic and things like that, you'll see that actually some of the optimizations that were in the original Kanren kind of been folded back in. So now there's not maybe as much as a distinction. But
is the original Kanren still under write?
No. So if you want to look at the original Kanren, you can find that on the SourceForge, and it's still up there. And it had some interesting ideas, but I think the original Kanren was very much modeled after Prolog, and if you don't know Prolog, it's going to be tricky. And some of the optimizations it did assumed, you were really familiar with the Prolog world. The other thing it didn't have that miniKanren now has is constraints other than unification. So now we've started turning it more into a constraint logic programming language, and I'll show you some of those sorts of things. Okay, so there's a lot of hand waving, like what does this mean? So let me just go ahead and show you. I'll show you the sort of the relational idea, and then I'm going to show you the miniKanren language, which is very small. The core language is very small, and then I'm going to show you some programs. And what I'm going to do is I'm going to start with scheme programs, and I'm going to turn those into miniKanren programs, and we'll see that you get some extra flexibility. Okay, and then what I really want to show later, we'll do a couple of examples. And then what I'd really like to show later on this evening is I'd like to show you what, for my money, is probably the coolest program I've ever been involved with. I think it's a really beautiful, interesting program. We're going to write a scheme interpreter in miniKanren, and we're going to see all the games you can play when you do that. It turns out it's like a really, really cool program. It's got some very surprising behavior. Okay, so that's the plan, unless people have objections to it. I'll tell you what I'm not going to show you. I can show you a little bit if people want, but I'm not really planning on showing this intention. A lot of people want to know, how does this magic work? They want to see the implementation, and that's a very interesting thing, but I don't really want to spend a lot of time on that for a couple reasons. If you do want to learn about the implementation, I guess at a high level, there are basically two things to know. First of all, miniKanren uses like a naive search. Basically, it's just doing a giant search over all these possible terms and things like that. You're building up all these constraints, and it's trying to solve them. And so the search is part of it. That's about half of the implementation, metaphorically, is search. And the way it's implemented is in terms of streams of values, like you might have in Haskell with these infinite streams. Basically, when you do a disjunction, an OR, you could have two different streams producing answers, two different expressions producing infinite sequences of answers. And the trick is, how do you combine those? How do you interleave the answers coming in? There are lots of different ways to do that. So that's part of the implementation. The other part is a two-way pattern matching called unification, which comes up all the time in computer science, but it's sort of the heart of Prolog style logic programming. And probably the best place to understand the implementation is this paper on this thing called miniKanren. And that's Dan Friedman and his current student Jason they've got this miniKanren paper that was in the Scheme workshop last year. And that paper builds up very nicely sort of the minimal implementation. The other thing you could look at is my dissertation, which is available online. That shows you, it goes in detail about how the unification is implemented and that sort of thing. Okay, so I'm not going to talk about implementation. The other reason I don't want to talk about implementation, other than the fact that it takes a while to talk about and there's some nice papers out on it, the other reason is that this really is very declarative, very high-level programming. And some people think, if only I understood the implementation, I would understand what miniKanren's doing and I'd understand how to write all the programs. No, you would not. Because the whole point is you're not supposed to know what miniKanren's doing. You're supposed to be writing at the very high level and you're saying what you want the program to do, not how to do it.
Sounds like a conspiracy theory.
A conspiracy theory. Yes, it is sort of a conspiracy theory. And it's a conspiracy theory where sometimes the answer to your program is yeah. So infinite loops, if you ever wanted to understand the halting problem, you're in luck. It's just sort of like Scheme. You learn Scheme to understand recursion, right? You learn logic programming to understand the halting problem. Okay. In fact, it's very difficult to write any non-trivial logic program that doesn't go into infinite loops for some inputs. All right. But anyway, we'll see all those fun things. So, yeah. So let's go ahead and get our miniKanren on. All right. So let's talk. Is that big enough, by the way? Is that back row? Do I need to make it bigger?
Good.
Good. Okay. All right. So let's go ahead and talk about what it means to be a function versus a relation. Obviously, lots of people here are interested in functional programming. Okay, and like I said, this is sort of a different take on things. And if you thought in terms of Prolog and logic, this might be a slightly different take on what you've seen in terms of logic programming. So let's think about, say, something simple like addition in Scheme. Okay, so plus 3, 4. I'll make it a little bigger. So obviously we have a prefix. Languages are beautiful S expressions. So let's say we restrict plus to take exactly 2 arguments. Okay, so Scheme's plus can take any number of arguments, but we'll restrict it to 2. So we've got a function. The function takes 2 inputs and has 1 output. Okay, and that's, as functional programmers, that's maybe the way we're used to thinking about things. But we don't have to think about addition that way, right? So a mathematician might describe addition very differently. They might describe addition as a tuple or a set of tuples, right? So you might say that the tuple 3, 4, 7 is part of this infinite set that represents all values, right? That you can that basically are generated through addition or something like that. So we can think of the generalization of addition. I'll put an O there because that's what we do in miniKanren land. So now we've got the relational version of addition, and it takes a 3rd argument. Okay, so we can think of this, actually we can put in a variable here actually. We could say X or Z maybe. Okay, Z is a placeholder, it's a variable, what we call a logic variable, that represents an unknown value. And if we ran this, if we had the definition loaded, which I don't, if we had everything running, then what would happen is Z would become bound to the value 7. Okay, so Z is unknown value, but it's just sort of like algebra, right? We'd fill it in and we get 7. Okay, so that's that doesn't seem very interesting because we could already get that answer back. Where it becomes more interesting, well, first of all, we can actually feed in the answer, and that will just succeed. It won't do any binding of any variables values. But we can also feed in a value like 348. And that's actually not legal because 3 plus 4 is not 8. So now we would fail instead of succeeding. Okay? So now we can already express things which are incorrect and have the system reject them. Beyond that, we can put a variable in another position. So we can say 3 plus y is 7. We don't know what y is. Well, y in this case is going to be 4. Okay, so that's something we could do that we can't normally do with addition in a functional language. Furthermore, we could do things like, say, x plus y is 7, right? And in that case, what would we get back? What would we get?
All the possible.
All the possible combinations of x and y that would give us 7. And how many are there? Infinite. So, like, what's an example of two numbers x and y that would give us 7? Negative 1 and 8. No, we don't believe in negative numbers.
What about 0?
0 and 7, that's one. We could believe in negative numbers, but I'm going to pretend I don't believe in them. Because I kind of don't believe in negative numbers. Anyway, yeah, but now that we have infinitely many answers potentially, or finitely many if we restrict ourselves to, say, the non-negative natural numbers, right? But if we really do want infinitely many answers, then we could just add a z there as well. And now we'll enumerate all the triples, right? All the triples of numbers, whereas x and y equal z. So now we've got a relational view of things where we can get more than one answer. We can express things which do not have a value, and that will fail. We can express things that do have a value without any variables in them. That will succeed. Or we can just put placeholders for things that we don't know, for values we don't know, and have the system fill them in. And I didn't tell you how this happens, right? I mean, I told you before that there's some search mechanism underneath the hood. But the point is, as a programmer using this plus relation, I don't have to give any special input. I just let the system figure it out. Okay, so that's a funny story. Let's see if it actually works. See if I can show you an example. All right, so let's make sure I got my numbers. Yeah, good. Turns out there's multiple ways to do this. I'll show you one. I'll tell you about the language in a second. I'm just going to give you an example. So let's do, I think I got my plus O here. Let's say build num 3, build num 4. So build num is just a scheme helper that will construct a number in a certain representation, because I didn't tell you how I represented my numbers. And then q is a query variable. So I'm saying I want one answer, run as my interface with scheme. I want one answer, q is my query variable, that's the variable whose value I want to know. And I'm going to say, I'm using this plus relation because in scheme, plus 0 actually isn't a legal identifier because of this scheme spec. But I'm going to say I want to add 3 and 4 and get some value q back. So if I type this right, hopefully it'll work. Oh, I think I have to load MK first. All right, let's see if this works. Yay, it works. Okay, now what can you tell me about my representation about numbers? They're lists of binary digits. Okay, so that's the representation of 7, obviously, right? So 3 plus 4 is 7. Okay, so if I called build num, what would be my representation of 4, for example? 1, 0, 0. Just like we said, 0, 0, 1. Okay, so why is it 0, 0, 1 instead of 1, 0, 0? Little endian, and why did we pick little endian for this representation?
So you have arbitrary numbers, significant zeros.
Yeah, the least significant bit is at the beginning of the list, the car of the list, first thing in the list. So if we want to add 2 lists, right, then we can just take the car of each list and add those things up. Okay, so that's our number representation. There are all sorts of other ways we could represent numbers and do this relational arithmetic. So there are also other ways where we just use normal scheme Arabic numerals and do this. Okay, but this just gives you an example of something, a number system implemented in core miniKanren. You can implement this in Prolog as well, where we just have lists of binary digits. And so I showed you it running forwards, as I call, right? So we said 3 plus 4 is 7, but we can also say that we know the output is going to be 7, right? And now we can say the query variable goes here, and sure enough, we get 4. And I can ask if there's a second answer, run 2. Well, I still only get the list of one answer, so that means that's a proof, that's a mathematical proof that there is no second answer. There's exactly one answer, no more. Okay? Like I said before, we could add 3 plus 4 to get 7, and that succeeds. Now our query variable q has this weird representation, _0. That means it doesn't have a bound value associated with it. That's just our convention. But we could also feed in something that's not correct. We could say 3 plus 4 is 8. That will fail. Notice we get back a list of 0 answers. That represents failure. There is no answer. There's no solution to this. Okay? There is no value for q for which 3 plus 4 is 8. Never holds. Now I can also do things like introduce a new variable. Let's say x and y and z. I'll have 3 variables here. And with those extra variables, now I can do things like put in x and y as placeholders for these 2 values. Actually, I'll get rid of z. So now what I'm saying is, I want to know a value of x and a value of y such that x plus y is 7. And here we really are using non-negative natural numbers. Okay, so we can have 0, 1, 2, 3, 4, 5. All right. Anyone predict what the answer will be when I run this?
A bunch of unbound variables.
What about unbound variables?
A bunch of unbound queues.
A bunch of unbound queues? Well, we have one answer because I only asked for 1. But yeah, if I ask for a bunch of those, let me do a run star. Yes, I get a bunch of unbound queues because my query variable q is the value I'm asking for, right? And I didn't associate q with the values of x and y. So x and y are getting values, but I'm never seeing them because it's only the value of q that I see for my query. So if I want to see what the values of x and y are, I have to associate q with a list of those. So I can say list xy is q. And now, because I did a run star is the same as saying, give me all the answers. Now I can see all the pairs of these natural numbers represented as little endian binary lists. Okay, so the first one, can anyone read what the first one is saying? Yeah, so this is 7 plus 0. Second one is 0 plus 7, right? And so forth. So we're getting all the pairs. Like this one would be what? That one is 3 plus 4. Okay? So we're getting all the possible pairs, and this is a proof that there are no additional answers. All right? Okay, that's fun. All right. So now, what's the answer to this? The answer is my fan will turn on in a minute. Infinitely many answers. Okay, cool. All right, so now here's a question. Let's say we want to add x and y. Okay, let's do it this way. Let's say I want to add, remember, we're only dealing with non-negative natural numbers, right? So 0, 1, 2, 3, 4, 5. They can't be negative. So we want to add 3 plus q, let's say. I'll go ahead and get rid of some of this stuff. So we're going to add 3 plus q, where q is our query variable. And we want that to sum to 2. So for what value of q does this hold? None, because we're restricting ourselves to non-negative integers. Okay, so there is no solution. Now if I hit return, what's going to happen? Okay, it could run for a little while. What else could it do? could give me back the empty list, or it could run forever. This is a very important point. It can only do one of the two. It can either go in an infinite loop or say there is no answer. All right? Let's see what it does. It says there is no answer, courtesy of the clever hacking of Oleg. Turns out that it's actually enormously difficult to write an arithmetic system that will guarantee this finite failure property is what it's called. In fact, in general, once you have logic and you have addition and multiplication, that's already undecidable. Okay, so individually we can say addition or multiplication is decidable, but it turns out that as soon as you start combining logical primitives and things like that, then decidability goes out the window. Okay, so we actually have proofs of decidability in a paper on this for the individual operators, but once you start combining them, that's no good. Okay, there is a restricted version of arithmetic called Presburger arithmetic, where you're allowed to have addition, and that's decidable. But once you start getting into anything that's sort of interesting, it's like already undecidable. Okay, so that one doesn't go in infinite loop, so great. All right, but anyway, this hopefully gives you some sense of the flexibility we get, right? So now we can start talking about, we can put placeholders anywhere, right? It doesn't matter. Basically, we've erased the distinction between input arguments and the output of a function, and now we've turned everything into a relation. We're allowed to treat all of those positions equally. The output is just as important as the inputs, and we can give an output and say what would be inputs that would give us that output. And when we write our interpreter, that will turn out to be really cool, because what we all say, the output of evaluating the scheme program is 7. Give me a scheme program that evaluates the 7. Okay, or enumerate scheme programs that evaluate the 7. Different way of looking at the world. Okay, so any questions so far?
Is it intrinsic to the system that it's limited to the sort of number sets? Is that?
Oh, I mean our number representation.
Yeah,
I mean.
well, yeah, and like some evaluated integers. Is that?
No, so we could represent numbers all sorts of ways, and we could allow negative numbers. We could have fractions, like rationals. We could deal. So I will show you another way of representing numbers in a minute, using what are called finite domain constraints, and that will allow us to get back our Arabic numerals. But it's a trade-off, because one of the things here that's nice about this numeric representation is these numbers can be arbitrarily large. The other thing is we can actually represent partial numbers, because remember, we can put in variables as placeholders. We can put the variables inside of the numbers. Okay, so we can have, for example, so instead of 3 plus q, okay, the number 3, if I build as a quoted list, would look like that, right? But what I could do instead, okay, so let me just show you what the representation and everything looks like. Okay, so that's 2. 3 plus something gives 2. Well, obviously, there's no answer there. But I could replace the 3 with something else. Let me show you what else I could replace it with. Now I'm using the back quote and scheme. And now I'm going to put in an x there. So I better introduce x as a new logic variable. But now what I'm saying is, I'll introduce x and y here. So what I'm saying here is that I've got some number, this weird looking thing, plus y, and that's going to give me back 2. Well, can anyone tell me what this number represents, or this weird term represents? 1.x?
Anything odd.
Anything odd, any odd positive integer. Okay, so I can represent all odd positive integers or any odd positive integers, the way I really should say it, using that single term. Okay, and now will there be an answer? Well, let's think about it. Is it true that there exists some odd positive integer that added to some other value will give you 2?
Yo, that's 1.
1 plus 1 would work, right? So let's see if that works. So let me make sure that my output, my query variable is associated with x and y. And sure enough, saying that we can add, so in this case it's saying that x has to be the empty list. And if this were an empty list, if you're familiar with scheme, that would make this term, if I make x the empty list, it's the same as 1 dot empty list, which is just the same as the list 1 in Scheme. So it's saying that the number 1 plus the number 1 gives you back 2. Okay, so it does have a solution. And you can play all sorts of games with variables in various places of the inside the numbers. Yeah.
So this strikes me. I mean, the sort of bit manipulation is very cool, but this seems to strike me as in some ways against the spirit of miniKanren, where you're actually caring about the implementation of these numbers. Like, wouldn't it be more ideal to think of the numbers as just the abstract Roman numerals, and then use some other functions like auto to deal with the constraints?
Well, certainly we're making explicit the representation, and you could wrap helper functions on top or come up with an abstract interface and things like that. There are actually many ways to represent numbers for these sorts of logic systems or relational systems. I'll show you one using Arabic. I think there's a tension there, because if you want to have placeholders, right? If you want to do what I just did, there are other representations of numbers where you could still say the number is odd, but there may not be a finite representation of all odd numbers, right? Or all odd integers. Okay, so there's a bit of a trade-off there. So you can still express it, but instead of having one answer come back, you might have infinitely many answers as it tries to enumerate them all. But you're right. And in this case, we are exposing the implementation of the integers, or representation. Yeah?
Does it have to enumerate all the possible sequences?
In this case, because we have a finite representation of all the evens, or all the odds, then we're okay. But if we wanted to, it doesn't have to enumerate everything. But there are other things we can't represent with this representation. Like if we wanted to do like all the prime numbers, right? There's not like a single term we could write down that we could have all the prime numbers. Or what if we wanted to do all the even numbers? Could we do that with a single term? Using this representation.
Could you use 0? Oh, no.
So it turns out that what we really don't want to allow, if we want to have a canonical representation of our terms, we don't want to have lists containing 0, because what we're going to really have say 0 is the empty list, and we'll say that you can have then a positive even number would have a 0 and then some other value, non-zero value in the most significant digit position. But in this case, you'd say things like it's either 0 as the empty list, or it's 0.x, where x has to be a positive number. So with this representation of numbers, we have different trade-offs. So when this is useful, it requires some expertise to know when this is the best representation.
It's like before when you were
Mm-hmm.
z plus 4,
Okay.
or x plus y to z, that's infinite.
Yeah.
Is you contemplating that from a lazy perspective? So I don't want it to enumerate
Sure.
all of them, I just want it to hold on with it.
That's a good question. So under the hood, there are a bunch of streams going on, and the streams really are lazy. When we ask for a certain number of answers, then we're forcing the streams. Okay, so
the run star was what was 40.
yeah, the run star is forcing it. So like in this case, I'll say we got X, Y, and Z. So there really are infinitely many answers, right? And now I can say, okay, so Q is the list of those. Now if I do a run star here, I really will get infinitely many. I mean, they'll never come back. But if I just ask for one answer, it'll say any number added to 0 will give back that first number. Is sort of how to read that answer, okay? So that's a very general answer. In fact, that answer represents infinitely many concrete answers, right? But there are infinitely many answers of this sort of form, right? So I could ask for the second one, or get 2 of them, right? And now we have something like this, which is saying that, actually, can anyone read this answer? What this one says?
0 added to
It's saying 0 added to
any number.
not any number, any positive number n for n greater than 0, right? Any positive number, then that is going to equal n. But so notice there's an asymmetry here, right? So this number actually has to be positive. So this is saying some bit dotted to some other number, which in fact has to be positive. So actually, no, in this case, this could even be the empty list. So this is like a weird representation of a positive number. And you can see the amount of fun you can have reading some of these answers, right? It can get out of hand, which is one reason you might want to use constraints to allow you to deal with just Arabic representation of numerals. And in fact, in Dr. Racket, I've got an example here, Dr. Racket, of the finite domain constraints, which go beyond the parts of miniKanren I've shown you. But in the finite domain constraints, we can do things like solve the classic send more money problem. Okay, and you can see here that actually we do have honest to goodness Arabic numerals like 0 and 9 and so forth. And here what we're doing is we're building up a whole set of constraints saying that the variable x has to be in this range, or the variable y has to be greater than 7 and less than 1023 or something like that. And you build up all these constraints with the numbers, and then you have a constraint solver that knows about finite domain arithmetic that will lazily try to solve things, okay? And so that's a different approach where you're trying to be as lazy as possible, build up a bunch of constraints for a particular domain, and then let the constraint solver solve things. Okay, so okay, that's fun with numbers. That's some hint of what relational programming is about, or treating programs as relations instead of functions is about. So let me go ahead and introduce you to the miniKanren language, the core language, which basically you've already seen at this point. So I haven't really gone into detail about some of the operators. So there's 3 core operators in miniKanren. One is called equal equal, which I usually pronounce unifies. The equal equal takes 2 arguments, 2 terms, and a term could be like basically any scheme value. So we can say equal equal 5 5, and you can think of it as an extended notion of equality or a type of pattern matching or term matching. We're asking, is it possible for these 2 terms to be the same syntactically? And here the answer is yes. So 5 and 5, they already are the same. So yeah, sure. And then we could also ask something like, are 5 and 6 the same? Or could they be made the same? The answer is no. There's no substitution of variables for values that are going to make 5 and 6 the same. There aren't even any variables that appear in that expression. Okay, so that's the simplest miniKanren program is basically this, where you're trying to see if 2 values or 2 terms are the same. If I try running it, I get back a scheme procedure, because miniKanren doesn't actually know about, or sorry, scheme doesn't know about equal equal. We have to wrap the miniKanren expression in a run interface. Some interface that will interface between miniKanren and scheme. So run is our query operator. So we always have run, and as you saw before, the first argument to run is some expression, some numeric expression. They'll tell you how many answers you want, or a star if you want all of them. And then we have the query variable, which could be anything. I could call that x if I wanted to. And as we already saw, if you have a miniKanren program, if that expression will succeed without binding anything to the query variable, then we'll see this _0 thing. And this is just saying some unbound value for the query variable x. We don't know what it is. It basically means it hasn't gotten an assignment through solving this equation, or solving these constraints or unifications or whatever. And furthermore, if I want to try to see if 5 and 6 unify, the answer is no. That's why we get back the empty list. Okay. I can also put in a variable, like the query variable, in that equation. So now I'm saying, can x and 6 ever be the same? And the answer to that is, depends on what x is, right? So if x is 6, then yes. If x is 7, then no. So in this case, we will succeed, but this only succeeds if x is also made 6. So that's why we see the answer coming back, a list with one answer back, saying that the query variable would have to become instantiated to 6 in order for this to hold true. Okay. We can also do multiple calls to equal equal, like a conjunction, logically, is like an and. So we want to say, is x 6? Can x be 6, and can x and 6 be the same? Yeah, sure, why not? Once x is 6, these both hold true, right? And we can also swap the order, right, and show that It's commutative. That's fine. However, if we say that x is 5, and then we try to see if x is 6, well, that can't possibly be the case because there's no assignment for x or no value for x that we can give it where x is going to be equal to both 5 and 6 at the same time, so therefore that fails. Okay? So that's unification. Unification you can think of as pattern matching. The important thing is you can actually have variables and arbitrary terms containing variables on both sides of the equal. So what I could do is introduce new variables. So fresh, which we've already seen, that's the second core operator in miniKanren. Fresh introduces new logic variables. So we could have x and y, let's say. Make this q my query variable again. And now, actually I'll just say, I'm going to unify x and y together. Okay, will that succeed? Sure. What's the value of x then?
Q is unbounded.
So q is unbounded, that's fine. Q doesn't get a value, but that's fine. That doesn't hurt anything. Okay, so q is just not involved, right? So as long as what we've written here inside the body of the run can be satisfied, then we'll get back some representation of q saying that it's unbound. Okay, so x and y, they can be the same thing. So what is the value of x? So let's see. Okay, I think I see what you're saying. So let's see exactly what x and y are, right? Making a list of x and y. Okay, so what do you think we'll see for x and y when we run this?
Unbound 1 and unbound 2.
Yeah.
Unbound 2.
Yeah, so now we have a list, unbound 1 and unbound 2, except we see unbound 0 and unbound 0. So what does it tell us about x and y?
They got value Q.
They have to be, well, for the list of x and y got bound to q, so that's the first thing we notice. Notice is the list containing a list of values, right? Well, what's the other thing? What do the zeros tell you? That they're both 0.
There's only one possible. Well, like per every unbounded value, it's the same in position.
It means x and y have to have the same value. So in order for x and y to be the same thing, if I tell you x is 5, now also y has to be 5. They have to have the same value. We haven't committed to a value yet, but we can commit to that through another unification. Let's say x being 5, right? In this case, we'll see that we have a list of 5, 5 back, right? That's exactly what we should expect because x and y have to be the same thing. That's what the first unification is saying. We're saying that these x and y forever are bound together. And in fact, there is a quantum computing or quantum physics metaphor. You can say that these two variables are now entangled and the state of one will influence the state of the other. In fact, there's actually a many worlds interpretation of logic programming, just like there's a many worlds interpretation of quantum mechanics. And that gets really interesting, but I'm not going to go down that path right now. So anyway, so now we're saying x and y have to be the same. X has to be 5, so therefore y has to be 5. Okay. So we've already seen two of the operators. We've seen equal or unification, and we've seen fresh, which introduces new logic variables. Also, fresh.
Question.
Yeah.
So in the run, everything was kind of like an implicit and?
Yes. So I was about to say that fresh also introduces a conjunction. There's an implicit conjunction, just like in scheme, lambda has an implicit begin, let has an implicit begin, fresh has an implicit conjunction, so these all have to happen in order. Or not you shouldn't really think about it in order, but they all have to happen together. Okay? Actually, order is something you should try to think about. Let's just try to forget about in most cases. And the same with run. So run actually has a hidden fresh in it, so it also has this conjunction in it. Okay? So logically, we have this notion of equality. Unification is basically a notion of syntactic equality. We have logic variables. We have conjunction. And the introduction of logic variables. So those are all things we've seen. So what are we missing logically? We've got conjunction, we've got variables, we've got equality. What's that?
Negation.
So we got negation. Oh, we forgot negation. Okay, that's kind of turned out to be a problem. We'll talk about that later. That's next month. Okay, I'll talk about negation a little bit. Turns out negation is the hard part. Negation is the tricky part. Okay, what else are we missing? Disjunction. Okay, so we don't have anything like an or yet. We've got an and, we don't have an or yet. So let's add that. And the disjunction is modeled on Scheme's cond. If you're familiar with cond from Scheme or Lisp or something, conditional, it's a way to have like a deeply nested or possibly deeply nested ifs with lots of cases, wrap it in a nice syntactic form. So cond in Scheme becomes cond E standing for every, getting every answer back, or every possibility, trying every possibility. So we'll have cond E. So let's say that going back here, where we're saying either x is, or here we're saying that we're trying to make x both 6 and 5 simultaneously, right? And of course there is no solution. But it's perfectly fine if we have one branch, like an OR where x is 5, another OR, another disjunct where x is 6. So we say x is either 5 or it's 6. That's fine. We can do that. So actually, let me write it this way. So cond E, like cond and Scheme, takes multiple clauses. You can use round or square parentheses in Scheme. I'm going to use the square ones to make the clauses stick out a little bit. Doesn't matter. So here we go. We've got, now we're saying that x could be 5 or x could be 6. But we're not saying anything about them at the same time. Okay, so if I wanted to get one answer back, what do you think I'd see? Either 5 or 6, right? I don't know which one. In fact, I shouldn't know which one, right? I should forget about which order they come back in. Okay, this turns out the first one's 5. If I do 2, I should get the 6 back, right? So now there are 2 possible answers, right? We're saying what are possible values for x?
I'll do 3.
What do I do 3? Uh-oh. What's going to happen if I do 3? You know there are only 2 answers. What's going to happen? One of 2 things will happen.
Run forever.
It'll run forever, right? Or it'll say there are no more answers, okay? And it says basically there are no more answers. It's saying, give us all the answers basically at this point because there's more than 2. So it's the same as writing a run star. So give us all the answers. There are only 2 of them, so that's why we get back a list containing 2.
Do you have a run operator that besides returning the result gives you the continuation? So
Good question. I have one. You can write your own through the power of Scheme macros. It turns out internally that's exactly how it works, actually. We generally don't expose that interface, but actually that's one thing I'd like to do is like have a whole set of operators that let you do those things. Like we would encourage people to play with that more, and the miniKanren paper talks about how that works in more detail. So for testing, for example, that turns out to be really useful. What's really useful is being able to have a run interface that ignores or having a testing infrastructure that ignores the ordering, right? So the fact that we have a list of 5, 6 coming back, you shouldn't think of that as in terms of the list. You should really think about that in terms of a set. It doesn't matter the order they came back in, okay? Arguably, we actually should return it as a set. So you shouldn't really think about the ordering of answers coming back. And there are lots of different approaches you could take for the interface operator, but because we're schemers, like I guess our somewhat flippant answer is write a macro or whatever, right? That's what we do. Okay, so that's it. So there's fresh to introduce new variables, and there's to add it to act as a conjunction. There's equal to perform unification of terms, and there's cond E that acts as disjunction. And that's it, other than the run interface, which is the interface between miniKanren and Scheme. And that's the whole core language, okay? So we get the 3 forms. Yeah?
So E, the suffix, that means for every array?
Yes.
And the O that you had before, that means one?
It kind of sounds like Spanish. Yeah, the O has nothing to do with one. Dan wanted something that kind of looked like a question mark when you squinted to sort of remind you of a predicate or something like that. It's kind of a goofy thing, but it does sound like kind of funny because you'll foo o or stuff like that. You translate foo into miniKanren.
First name operator.
What?
Plus operator.
Oh yeah, plus O and stuff like that. Yeah, so basically it's just a way that, because what will often happen is if you're translating Scheme to miniKanren, or you're embedding miniKanren inside of Scheme or Clojure or something like that, you'll have a mixture of miniKanren predicates and Clojure functions or something like that, right? Or core.logic and Clojure. So by having that convention, it just like sticks out, but it's not really necessary. It's just something we use for the book that was kind of cute. Yeah, so. Okay, so now let's write our first honest-to-goodness miniKanren program, and we're going to base it on a Scheme program, a very complicated program called append. Okay? Anyone remember append and Scheme? Let's see. Define append, lambda. How many arguments does append take? Everyone remember what append does? It takes two lists and appends them together, right? Concatenates them. Okay, so L and S, let's say, are the two lists. Okay. No, now what do we do with append?
If null L, then
All right, if, well, we could write if, but we're going to use con because it's recursive. So, okay, so how many clauses are we going to have? So we had a null test.
null case and
The other case, the null test.
and the inductive.
Yeah, so we have a base case and one recursive case. Okay, so we have two, and so the test is going to be null on L. Okay, so if the first list is empty, then what are we going to return? The second list, right? Okay, easy. Now, in the second case, else case, now what are we going to do?
Cons the car of L to the.
We could do that. That sounds really complicated. We could do that. Sounds really complicated. So, is it going to be recursive or not? Has to be, because the list could be arbitrarily long, right? So we're going to make a recursive call, right?
What to append
So we're going to append what?
the cover of L.
So we ask the question about L. If it's null, so we have to get closer to the null case, right? So we take the cdr, get the rest of the L, okay? To what? Did we ask any questions about S?
No.
Nope. So S doesn't change. So we have a working definition, right?
We got
Not quite.
Cons the car
Okay, so
onto the pen.
so some people will know functional programming. We could just jump to the end. But if we're being noobish about it, right? We write the natural recursion, then of course cons it on when that doesn't work, right? Okay, so there's our definition of append, right? And let's see, I'm going to use lists of numbers here. Let's try that. Sure enough, seems to work. Okay, so now we're going to write not append, but what?
Appendo.
Appendo, of course. Right, appendo. Okay, so now what do I write first? Lambda, of course. What arguments are going to take? L, S, and R. What is R? Just because it comes after S. Does S come R? Q, R, S? Yeah, it sounds like. Okay, so result is good. So let's call it out, which is a horrible name, but because if you think out, then you'll think there's something special about it, right? But there really isn't in relational world. I'll call it out anyway, just for convention. But we could call it R. We could call it whatever we wanted, right? Okay, so the point is we have one extra argument which represents the output of the function, right? Now it's actually an explicit argument. Okay, so we could call it R. That'd be cool. I'll call it out just because that's what we do in the book, I think. Okay, so we had con before. What's it going to be now? Con D, right? Okay, cool. And we had two clauses before, so we'll have two clauses now. Easy. All right, so we had this null test. I didn't show you like nullo or something. We could define nullo. What operator do you think null would this null test is going to equal? So we can see if it matches, right? We say, does L match the empty list? Okay, and this is a little different. This is stronger than matching, because if L is an unknown value, now L is the empty list. So this also can act as an assignment. So it's either matching or an assignment. And if an assignment is like a single assignment, okay, we're not allowed to ever change its value from that point on. It can become more instantiated, right? If it's like a list of some other unknown values, those values can become more and more instantiated. But once we decided it's the empty list, it can never be 5 from then on or something like that, okay? All right, so that's the equivalent of our null test. is to see if L unifies with the empty list. Basically, we're asserting that L had better be the empty list, and if not, that line of the conD is going to fail. We'll try the other one. Okay, we'll try the other one anyway. Actually, that's the weird part. Okay, so before we returned S. Well, we're not returning anything anymore in the world of relations. So instead of returning S, what would we want to do? You unify S and L. Okay, so now out and S are the same thing. So we're not returning values anymore. Now we're unifying things. Okay, cool. Now we get the second clause. Second clause is a little more complicated. First of all, it has this else thing. Ain't no such thing as else in logic programming. We try every clause all the time. Always be trying every clause. So that's gone. Turns out that negation thing. Well, what does else actually mean? You ever think about what else means? What does else mean? If I rewrote this instead of else,
Every condition.
yes, that's the same as not null, right? There's a negation in there. Oh, uh-oh, that's nasty. So it turns out in this case we get lucky. Why did we get lucky? Because it turns out that we're going to do some unifications that basically mean, so not null we can interpret in this case as it's a pair, L is a pair. Okay, and we'll do some unifications that enforce that L is a pair, and that will kind of get us around that. But there'll be other cases where you have an else, and that else is really tricky to implement. You might actually have to write a whole other relation as a helper because of that else, or one of the other tests in the below a test and a con. So that could be tricky. But we're getting rid of the else. Turns out we could add this not. It's not really necessary. It's like the opposite of not would be something's a pair. Well, we can ignore that for right this second. I can tell you that because I've written this a bunch of times, but part of this is just practice. Okay, so we have something like this. We have consing of car to append, coder, that sort of thing. So notice we're taking cars and coders. So once again, just like with the null, I didn't tell you how to take the car and the coder. We don't need car and coder. We've got the giant 800-pound gorilla wielding a sledgehammer, right, called unification. And that's going to be our big beast. So instead of getting, how do we get the car of L then? How do we get the coder of L? You're going to unify it. Yeah, so we're going to unify L with what? A pair that has a car and coder, right? So we could say A and D, cons A and D onto each other. Now, in order to do that, we're going to need some logic variables, right? So fresh A, D. There is a pattern match. If you're familiar with Prolog, there's a pattern matching notation you can use in miniKanren that will introduce the A's and D's automatically in certain cases. But I just want to show you kind of the elementary view of things. Okay, and in fact, if we were writing in kind of the canonical miniKanren style, instead of putting the explicit cons, we would just have a dotted pair there. So it kind of looks like what scheme would print out. So here we're saying L has to be a pair of some value A. The car is A and the coder is D. Okay, so now we know L is a pair, so that takes care of our not null test, right? And furthermore, the car of L, we can give that a name now, that's A. The coder of L, we can give that a name now, that's D. So we've already taken care of that aspect. Now we have this recursive call we have to deal with, right? So let's pull that out. And what's the name of that recursive call? That's not going to be append, that's going to be appendo. That takes 3 arguments, not 2. So we need a placeholder. So the value that would normally be returned from append, now because append takes 3 arguments, the last of which represents sort of the output, we need some temporary value. So we call it temp or something like that. We call it res usually, like for result. Okay. So when we call appendo, that's going to give us back some result associated with res. And then finally, we've got our cons here, cons A onto res, and that is what we return, but of course we never return things anymore. Instead, how do we return the value of that cons? Unify without, right? Okay. And if I really want to be miniKanren-y about things, I'll get rid of the cons and replace that with the pair. Okay, so that's our definition of appendo. And let's try it out. Let's give this a try. Hopefully I didn't mess anything up. So let's just try something simple, like what we had before. So we're going to say appendo. Once again, we had list 1, 2, 3 and list 4, 5. Sure enough, it works. Great. Okay. Now, what else can we do? That was a lot of work to do append, right? What can we do now? We have our fancy append.
You could
Go backwards. What does that mean?
So, give an answer.
yeah, 1, 2, 3, 4, 5 is Q, and then a fraction
Okay.
in Y.
So we could do it a couple ways, right? So like we could just put a Q here, and we could say the answer is 1, 2, 3, 4, 5, right? Like that. Whoops. So what should we Q be now? 4, 5. Okay, cool. All right. What would happen if I put run 2 there, by the way?
You'll get one less. Oh, yeah. Run forever. Well, it's not a set union, so it would be only one result. I think.
There may be only one answer, but that's not what I asked. That's what will happen when I run it. So this is an important point. Just because there's only one answer doesn't know that miniKanren knows there's only one answer, because if it's doing a search, right, everything kind of has to align or be written in such a way that it will figure out there's no more answers, right? So let's try running it. Ah, that one worked. Okay, phew. Huh, now. Okay. Let's try that one. Putting the Q in the front. Okay, so Q should be 1, 2, 3. Works like a champ. Run 2. Any thoughts?
I think it's going to return.
I think you're wrong. Oh no. I did set you up. Okay. So what's wrong here? What's wrong? Can we get back? Can we get back some better divergence behavior? Okay, so here's our definition of appendo. By the way, I mean, append is a simple thing, and in Prolog it's like the hello world example, but it's actually really subtle. There are a lot of very interesting things going on with append. If you really, really understand append, you understand most of Prolog style logic programming in a very, the pure stuff actually. Okay, so why, is there anything we can do to this program to improve it so that that program won't go in infinite loop?
So is there, can you do a clause that unifies S with empty list?
S with empty list?
Or I guess that doesn't work.
Well, we could have more special cases, but the problem is going to be in our recursion, right? So, any ideas what we could do here?
Limit the length.
We could try taking length. We could do that, and that's a very good idea. We can add extra bounds. Do you know what happens when we try to do that if we are naive? Taking the length goes in infinite loop. I'm not kidding. That's exactly what happens. So we can't do that. What? Well, we don't have to do that though. It turns out there's something much simpler we can do. Ready? See that? Oh, you miss it? I'll try it again. Ready? Ta-da!
I thought order didn't matter.
Yeah. That's
Okay, so order doesn't matter up to a point. Let me tell you about order. Let me show you how this works, by the way. Okay, so
It allows you to prune. You're pruning by evaluating your constraints first.
yes, but I'm safely pruning,
Yes.
right? I'm saying I know there's no answer down here. Okay, so declaratively it's the same exact information, but miniKanren can take advantage of that information sooner. So here's the thing about ordering. You notice, in order to get the infinite loop, I had to do a run 2, not a run 1. That's the key. I can reorder these things any way I want. So for example, the worst possible ordering would be to put the recursion first instead of last, okay? In fact, I can even reorder these and all that sort of thing, okay? So this is kind of like the maximally bad ordering of things, because those unifications won't happen until after the recursion. So the recursion doesn't have any information to try to cut off the search. Okay. I can go back to our thing that was giving us trouble, our example was giving us trouble. As long as I only ask for the one answer that exists, it'll find it. If I ask for the second answer, which does not exist, that's when I get into trouble. Or if I ask for one answer that doesn't exist, so for example, I can say, ABC, right? There's no list Q that when appended ABC gives you the list 1, 2, 3, 4, 5. There is no answer to that. And I'm only asking for one answer. The answer doesn't exist. That will go in an infinite loop because what's happening is that the search is just looking forever and it never knows to cut itself off. By reordering the clauses here so that the recursion comes last, I can even have the Condi clauses swapped like that. That's fine. miniKanren doesn't care. So as long as I have the unifications happening before the recursion in this program, then we'll cut off the search and figure out there is no answer. Okay? So that's where the ordering matters. There are two ways in which the ordering matters. First of all, there could be efficiency. It could be that in order for miniKanren to find the answer, it has to search billions or trillions of nodes or whatever. I have to really search hard in this big search tree. In that case, the ordering could matter because maybe you'll find it sooner or later. But the big one is whether or not it will search forever versus searching finitely, having this finite failure. And so the bottom line is, if the answer exists, miniKanren will find it in theory. Might run out of memory first or whatever, but in theory it would find it. If there is no answer, it could go into an infinite loop, or it could fail finitely after some finite amount of search time. It will return an answer saying that there's nothing left to find. Okay, and ordering matters there. So if you're looking for an answer that does exist, you'll find it regardless of the ordering. Okay, it's a kind of a subtle thing, but you're running up to the halting problem with this. Okay, so that's appendo. So the hello world, append is a hello world of logic programming. I should say one more thing about this running into infinite loops, finding answers. What I say is only true about the miniKanren search, about if there is an answer, you will find it eventually. That's not true of Prolog, standard Prolog, because Prolog uses a depth first search where it tries to go down one branch of the tree, like one branch all the way down to the end. It turns out that sometimes those paths are infinite, and it will, the answer will be like right up here at the top of the tree. But because it's doing a depth first search for memory efficiency, it will never find it and it'll go to an infinite loop even if you have the solution. Okay? So that's an incomplete search. miniKanren uses something closer to breadth first search. We use more memory, but the search is complete. If the answer exists, we will find it. Okay? There are other search strategies like incremental deepening that do more work. You repeat work, but you get completeness and you get the low memory usage. So there are lots of different ways to search. There are heuristic searches you can use in some cases, that sort of thing. But this is very much a search problem, and it can be parallelized as such. Yeah?
So if you know that basically your constraints for unification, if you have them before recursion, you can't just reorder that in the library?
Ah, good question. Okay.
If you know that that's always true, then
Yeah. So we can do that, and you could write a compiler, or you could do things like that, right? And that is absolutely true. The trick comes in when you have multiple recursions. Then there's no way to put them all last. And then it does get tricky. But you're absolutely right. So what Dan likes to call Will's law is put the unifications before the recursion, right? So that's just kind of common sense. No reason not to do that. But when you have multiple recursive calls, then they can't all come last, and that's when it gets tricky. But you're absolutely right. You want your unifications to come before your recursions. Yeah.
So this is probably a stupid question, but could this could relational programming be used to find local minimums? Like if you find a goal of some algorithm, and then and it could find like n local minimums for you.
So with the constraint logic programming, with the finite domain constraints, if you look at the more sophisticated implementations of those, they often have min and max solvers. So you build up a bunch of constraints on the numbers, and it will actually it will minimize or maximize formulas for you. Wow. So you actually can do that. And the cool thing about the finite domain constraints or any of these more advanced constraints is they can be really efficient. They can be more efficient than what you would write in hand by C because they can take into account all this knowledge of the domains and stuff like that, right? So if you can map your problem onto something that works with one of these constraint solvers, it's sort of like mapping it onto a SAT solver or an SMT solver or some fancy thing, right? Like you can do better than a naive human would do writing it in C, that kind of thing. So you can get really good performance. On the other hand, those domains are very narrow, and you may not be able to map your problem on, or you might have to do all sorts of weird encoding rules, or like kind of the numbers, the Oleg numbers, right? That's kind of this weird way of encoding numbers that lets you do things. That can come up.
So, as an example, could you write a logic program to suggest chess moves?
So that's a good question. You should be able to do things like retrograde analysis and things like that. You have to be careful not for the search, to make sure the search space doesn't blow up. So part of that, if you could,
That first seems like a good idea in that case. Sure.
it could be, although you could run out of memory because of that. So some sort of search, like incremental deepening, could also do that, where you are going to guarantee you'll hit the first answer in the tree, not something like much further down. So that certainly could be possible. And like I said, if you can map that problem, if you can rewrite it into something that matches onto the finite domain constraints, then you're good to go. A typical example is the n-queens problem, speaking of chess puzzles, right, where you have trying to put 8 queens on a chessboard so that they don't attack each other. That's exactly the sort of thing you could encode with finite domain constraints. And so to give you the racket example here, there's this famous logic puzzle called Send More Money, where it's a cryptarithmetic problem where you have SEND up top and MORE and then equal line and then MONEY. So each letter represents a variable with a value between 0 and 9. And you're supposed to figure out what are the assignments of these letters representing variables to the values, the numbers, that would make this formula add up and make this word problem make sense. And that's the sort of thing you can do with finite domain constraints. So for example, if you look at the racket version of miniKanren, that's one of the examples that comes to it for finite domain constraints. And you can also this diag. Okay, so here's actually, I think this is diag. Yeah, so this is the n-queens problem, for example. Yeah, so you can represent this using here's a little function that looks at the diagonals, and you can see that here we have some constraints, like a plus constraint, like we saw before, but this one actually is using an honest to goodness constraint solver over numbers. And we also have things like NFD, this is saying that these 3 variables are within this finite domain range, or actually these 2 are within the range of this finite domain and so forth. So you can express these problems fairly succinctly and make them run fast. And things like Sudoku work really well. Yeah.
Is that different from like a Prolog implementation?
Yeah, so in Prolog, so the problem is Prolog uses unification as its main constraint, so the equal, and you could do something like the Oleg number representation. Here, this constraint solver is more like something like a SAT solver or an SMT solver, something that has very specific knowledge about a certain domain, like in this case, domain of non-negative integers. And so it knows about a few operators like less than equal, addition, multiplication, things like that. So it's not very general, but it's very, very fast, and it can delay evaluation of the constraints until it has enough information to get a single solution instead of enumerating them all. So once again, it's a set of trade-offs. So the Oleg arithmetic system, the Oleg numbers I showed you at the beginning, in some ways they're more general. You can represent arbitrarily large integers, things like that, but it's generally less efficient. And if your problem maps onto the finite domain constraints, like this thing could be super fast. So David Nolen I watched a video recently of someone from some sort of JavaScript convention showing core.logic running under Clojure script in the browser, doing Sudoku puzzle on apparently some particularly difficult Sudoku puzzle, and it was doing it in JavaScript in a couple milliseconds. So that's what you can do with a nice finite domain solver. If you tried encoding that with the Oleg numbers, it would, who knows how long it would take, but it'd take a lot longer than that. The other thing that's really nice about using these constraints is that the reordering turns out not to affect efficiency nearly as much. So, when you're writing a regular miniKanren program, the reordering could affect the divergence behavior, the infinite loops, and it could also affect how long it takes to run things. When you're using the finite domain solver or one of these other constraint solvers, turns out you can reorder things any way you want, and the performance is extremely stable. So maybe off a few milliseconds, but But otherwise, so those sorts of problems, like if you want to write a Sudoku solver, it's a few lines of code in miniKanren, and it's really fast. You'd be hard pressed to write one by hand that'd be as fast as the miniKanren one, even though it's super short. So that's nice. But if you want to do something that doesn't quite map on, then it's going to be a lot trickier.
You were saying different search regimes. Can you actually configure miniKanren to do different kinds of search?
Some people are starting to play with that. There's a paper in the last Scheme workshop about using a guided search, and it's easy to do things like implement a depth first search that's incomplete. We've played around with a few search strategies. I would like to have a nice implementation of iterative deepening, where you basically like a depth limited search where you keep increasing the depth over time. That would give you good memory performance, but at the cost of redoing some work. I would like to see more people explore that. I'd like to explore that more. There's a system called CiaoProlog, CIAO. That's really neat, and it allows you to parameterize the searches by modules or different parts of your program. So you can have part of your program have depth first search, and part of your program have breadth first search, and part of your program have IDDFS, and that's like a really snazzy thing. So I would like a system like that in miniKanren. That'd be really cool. Yeah. Okay. So I don't know how long we've gone here. So I've shown you a simple miniKanren program and the basics of miniKanren relational thinking. We could go a couple ways now. One thing we could do is take a little break, and we would go to the bathroom, we get something to drink, and then we could take off and pick up in a few minutes and do the interpreter, or people keep going if we want, or what do you think, Ben?
People want a break? They're good. Yeah.
Yeah, let's take a break. Okay. Cool.
Okay.